Imagine for a moment that you could compress the entire history of Earth into a single year. Every second would represent 146 years of real history. On this compressed timescale, our planet formed on the 1st of January. Life emerged at the end of February. The dinosaurs appeared in the middle of December and went extinct on the 26th. And humanity, we would appear in the last 4 minutes of the 31st of December. 4 minutes. That is all we represent in the vast temporal symphony of our planet. But here is the question that keeps some scientists up at night. What happened during the other 365 days? What stories were written and erased in those vast stretches of time before we arrived? It is possible that other intelligences, other civilizations, may have flourished and vanished in the previous eons, leaving behind barely whispers in the rocks that we no longer know how to listen to. This is not science fiction. This is a legitimate question that emerges when we truly grasp the timescales with which our planet operates. Scales so vast that our human mind can barely begin to comprehend them. Scales where entire civilizations can arise, flourish for millions of years, and disappear without leaving any trace whatsoever. Tonight, I invite you on a journey through deep time, a journey where we will explore how the Earth itself becomes a memory-erasing machine, like the pages of a book that are rewritten over and over again. We will discover why the absence of evidence is not evidence of absence, especially when we are talking about temporal scales that make all of human history seem less than a blink. Are you prepared to contemplate the possibility that we are not the first to call this blue planet home, to confront the cosmic humility of recognizing that perhaps we are only the latest in a long chain of civilizations that have contemplated these very stars? If these kinds of slow-burning questions are your kind of questions, I would be grateful if you would subscribe to Data Terra, because on this channel, we believe that the best questions are those that do not have easy answers, and that mystery is not something that should be quickly solved, but something that should be slowly savored, like a fine wine under the stars. So settle in, take a deep breath, and prepare for a journey that will forever change the way you view time, the Earth, and our place in this cosmic story we are only just beginning to comprehend. Have you ever truly tried to imagine how long humans have existed? I do not mean knowing it intellectually, but feeling it viscerally in your bones, in your deepest understanding of time. We are a species that measures time in days, weeks, years. Our lives span decades, our civilization centuries, perhaps millennia if we are lucky. But the Earth thinks on completely different temporal scales. Let me help you visualize this in a way you may have never considered before. If you were to represent the entire history of the Earth as a highway stretching from New York to Los Angeles, approximately 4,500 kilometers, each kilometer would represent 1 million years. On this scale, the entire existence of the genus Homo, from our most ancient ancestors to us, would occupy only the last 3 kilometers of the journey. And our modern civilization, the one we are so proud of, with our cities and technology and art, that civilization would occupy less than 1 meter at the end of that highway. 1 meter in a journey of 4,500 kilometers. Think about that for a moment. Let that image settle in your mind. But there is something even more astonishing. For most of that highway, for thousands and thousands of kilometers, life not only existed, but it evolved, experimented, diversified in ways we can barely imagine. There were periods of complexity and sophistication that rival anything we have seen. Consider the Cambrian period, about 540 million years ago. On our temporal highway, this occurred about 540 kilometers from the end. During this epoch, known as the Cambrian explosion, life experimented with body forms that seemed to be taken from the most creative nightmares of a surrealist artist, Anomalocaris. A predator the size of a bus, with giant compound eyes and grasping tentacles. Aishia, a creature so strange that paleontologists initially did not know which was its top and which was its bottom. Opobenia, with 5 eyes on its head and a proboscis ending in a claw. These were not primitive creatures. They were the result of millions of years of sophisticated evolution with complex nervous systems, elaborate hunting strategies, and adaptations that speak of an evolutionary intelligence operating with a logic completely different from ours. Or think of the Devonian period, about 400 million years ago. The oceans were teeming with life. Armored fish the size of buses patrolled the seas. The first forests spread across the continents, creating ecosystems of a complexity that took millions of years to develop. If a form of intelligence had arisen during this period, it would have had 150 million years to develop before the dinosaurs even appeared on the scene. 150 million years. To put this into perspective, that is 500 times longer than we have existed as a species. What could a civilization accomplish with 150 million years of continuous development? We have gone from stone tools to space travel in less than 10,000 years. What would others achieve with 15 million times more time? But here is the truly disconcerting part. We find no trace whatsoever of such a civilization. The Devonian oceans are full of fossils of armored fish and ancient corals, but there is no evidence of technology, of construction, of conscious alteration of the environment. Does this mean that such a civilization never existed? That is the obvious conclusion, the one most of us would accept without question. But what if the question is not whether they existed, but whether we would be able to detect their existence after so much time? Think of it this way. If our civilization disappeared tomorrow, what would be left of us after 100 million years? Our cities would erode into dust. Our steel would oxidize and return to the earth. Our plastics would decompose under solar radiation and microbial activity. Even our most dramatic alterations of the landscape, our largest dams, our deepest mines, would be barely minor irregularities in the geological record after plate tectonics, volcanoes, and glaciers did their work for millions of generations. What would remain? Perhaps some anomalies in the isotopic composition of certain rocks, maybe a thin layer of synthetic materials compressed in some geological stratum, possibly some changes in the global distribution of certain chemical elements, but unequivocal evidence that we were a technological civilization, evidence that an alien geologist would find obvious after 100 million years. Probably not. And if that is true for us, with all our technology and our global impact, how easy would it be to detect a civilization that flourished 200 million years ago, or 400 million years ago, or even longer ago? The answer is unsettling. It could be virtually impossible. We are accustomed to thinking in terms of preservation when we consider the past. The Egyptians built pyramids that have lasted thousands of years. The Romans built roads and aqueducts, whose remains we can still see. But those are temporal blinks, less than microseconds on the geological scale. On the real timescales of our planet, preservation is the extraordinary exception, not the rule. The norm is destruction, transformation, the constant recycling of materials through processes that operate with a patience that defies human comprehension. We begin to glimpse the magnitude of the problem. It is not that there has not been enough time for other civilizations to emerge before us. It is that there has been more than enough time for them to emerge, flourish for periods that dwarf our entire existence, and disappear so completely that we could barely detect their most subtle traces. And those subtle traces, well, would we know how to recognize them if we saw them? That is a question we will explore as we delve deeper into this temporal journey, because it turns out that the Earth is not only ancient, it is also an extraordinarily efficient, memory-erasing machine. And to understand why we might not be the first, we must first understand how our planet systematically devours the evidence of its own past. There is something profoundly unsettling about the idea that life on Earth has been almost completely erased at least 5 times in its history. We are not talking about minor events, about small disturbances in the course of evolution. We are talking about nearly total reboots, moments when our planet literally became a death machine that eliminated up to 96% of all living species. Imagine this. You walk through a bustling city, full of life, of activity, of millions of intertwining stories, and then, in a period that can last from a few years to a few millennia, practically everything disappears. The buildings remain, perhaps, but empty. The streets are there, but silent. Occasionally, you find a lost, disoriented survivor, trying to understand what happened to the world they knew. That is what mass extinctions have done to life on our planet. Not once, not twice, but repeatedly throughout its history. And each time, life has had to reinvent itself from practically scratch. The most famous, of course, is the extinction that wiped out the dinosaurs 66 million years ago. But that was not even the worst. It was merely the most recent of the 5 great ones, as paleontologists call them. The worst of all occurred 252 million years ago, at the end of the Permian period. Scientists call it the Great Dying, and it is a name that does not exaggerate at all. This extinction eliminated 96% of marine species and 70% of terrestrial species. Imagine, out of every 100 species that existed, only 4 survived. But here is what I find most fascinating and also most disturbing. Each of these mass extinctions not only erased existing life, but also erased the evidence of what had come before. Think of it this way. When a mass extinction occurs, it is not just that animals die. Entire ecosystems collapse. Sedimentation processes change dramatically. Weather patterns are altered. The oceans become acidified or anoxic. Continents can be covered in volcanic ash or devastated by acid rain. In those conditions, what chance does any delicate evidence have of being preserved? What chance does an artificial structure, an artifact, even a fossil, have of surviving not only the initial extinction, but also the millions of years of extreme conditions that follow as the planet recovers? Let us consider the Permian-Triassic extinction in more detail. Scientists believe it was caused by massive volcanic eruptions in what is now Siberia. These eruptions lasted approximately 60,000 years and covered an area the size of Europe with basaltic lava. But it was not just the lava that caused the extinction. It was the gases released, carbon dioxide, that caused extreme global warming, sulfur dioxide, that created devastating acid rain, and halogenated compounds that destroyed the ozone layer. During those 60,000 years, the Earth turned into an inferno. Ocean temperatures rose so high that the deep oceans became anoxic, oxygen depleted, turning into enormous dead zones. The continents became arid deserts, battered by sandstorms and acid rain. In those conditions, even the most durable materials would disintegrate. Metal would corrode until it disappeared. Ceramics would crack and erode. Even work stone would wear down until it became sediment indistinguishable from the natural. And that is just one extinction. There have been 5 this severe and dozens of minor extinction events. Each one represents a nearly complete reboot, not only of life, but of the preservation of evidence from the past. But there is something even more unsettling to consider. What if mass extinctions are not random events, but part of a wider cyclical pattern? Some scientists have proposed that mass extinctions occur in cycles of approximately 26 million years. If that is true, then the Earth not only periodically erases life, but does so systematically, like a gardener who regularly prunes to allow new growth. In this unsettling scenario, mass extinctions become more than cosmic tragedies. They become evolutionary opportunities, moments where life can explore new directions, new possibilities, new forms of intelligence. Imagine a civilization that emerged in the period after a mass extinction. It would have millions, perhaps tens of millions of years, to develop before the next great reboot. That is more than enough time to evolve from stone tools to technologies we can barely imagine. And then the next mass extinction arrives. No matter how advanced that civilization was, no matter how sophisticated its technologies were, if they had not developed the ability to survive a complete planetary reboot, they would simply disappear. Their cities would disintegrate under the heat and acidity. Their technologies would corrode into basic elements. Their very bones would dissolve in the acidified oceans. And after millions of years of hellish conditions, when the planet finally stabilized and life began to recover again, what evidence would remain that that civilization had ever existed? Perhaps, if we are lucky, some chemical anomalies in the rocks, perhaps some isotopes in unusual proportions that might suggest industrial activity, possibly some synthetic minerals that survived the extreme conditions, but unequivocal evidence of intelligence, something that would scream to us. A civilization was here, probably not. And here is the part that truly keeps scientists awake. We exist in the period after the most recent extinction. The dinosaurs disappeared 66 million years ago, and we emerged in the world that developed in the vacuum they left. But what happened in the periods following the other 4 great extinctions? What forms of life? What types of intelligence? What civilizations could have emerged and flourished in those other post-apocalyptic worlds? The Ordovician-Silurian extinction, 445 million years ago. The late Devonian extinction, 375 million years ago. The Permian-Triassic extinction, 252 million years ago. The Triassic-Jurassic extinction, 200 million years ago. Each of these represents not only a cosmic tragedy, but also an evolutionary opportunity. A world that reboots, that starts anew, that offers new possibilities for the development of intelligence. And we are just the latest in line, the latest to inherit a post-extinction world, but the first to develop intelligence, the first to build civilizations, the first to contemplate the stars and ask ourselves if we are alone. Perhaps, or perhaps we are simply the most recent in a long chain of civilizations that have arisen, flourished, and disappeared in the recovery periods between the great planetary reboots. The difference is that we are the first to realize that the reboots exist, the first to understand that our planet has a history of systematically erasing the slates of life, the first to ask ourselves what was lost in those previous erasures. And that awareness might be what allows us to be different, what allows us to be the first to survive the next great reboot. Instead of simply being another civilization that disappears among the rocks of deep time. But to truly understand the implications of this, we need to explore more deeply the exact mechanisms by which our planet erases the evidence of the past. Because mass extinctions are only the most dramatic method. The Earth has many other ways, more subtle but equally effective, of making the traces of its oldest secrets disappear. If mass extinctions are the great hammer blows that erase the slate of life, ordinary geological processes are the artists of slow erasure, working silently, day after day, year after year, millennium after millennium, until even mountains turn to dust and oceans turn to deserts. The Earth is not a museum. It is not an archive that carefully preserves the artifacts of the past for future generations to discover. The Earth is a cosmic recycling machine, constantly chewing and regurgitating its own surface, transforming rock into sediment, sediment into rock, ocean into continent, continent into ocean, in an endless cycle that operates on temporal scales that make all of human history seem less than a sigh. To understand why we might not find evidence of previous civilizations, we need to understand these processes. We need to see the Earth, not as the stable, permanent planet it seems in our human lives, but as the dynamic, violent, and transformative world it truly is when we observe it on geological timescales. Let us start with something seemingly simple: erosion. Think of the highest mountains you know, the Himalayas, the Alps, the Rocky Mountains. These formations seem eternal, immutable, the very bones of the Earth. But from the perspective of geological time, they are temporary structures, sandcastles that the wind and rain are constantly demolishing. The Himalayas, the world's highest mountains, rise approximately 5 millimeters each year due to the continuous collision between the Indian and Asian tectonic plates. But at the same time, they erode at a rate of approximately 2 millimeters per year. In net terms, they are growing, but they are also constantly being gnawed away by the elements. How long would it take for them to completely disappear if they stopped growing? Approximately 15 million years. That is all. 15 million years for the world's highest mountains to become soft hills, and another 15 million for those hills to become plains. Now imagine a civilization that built its greatest monuments on those mountains 100 million years ago. No matter how large those structures were, no matter what materials they were made of, they would have been completely erased by erosion long before the dinosaurs even evolved. But erosion is only the beginning. It is the most visible process, but not necessarily the most powerful of the terrestrial mechanisms of oblivion. Consider sedimentation. Every year, the world's rivers transport approximately 20 billion tons of sediment from the continents to the oceans. 20 billion tons. That sediment has to go somewhere, and where it goes is on top of everything that was already on the ocean floor. In areas of high sedimentation, such as the deltas of large rivers, deposit rates can be several meters per century. In the Mississippi Delta, for example, sediments accumulate at an average rate of approximately 3 meters per every 1,000 years. That means that anything that was on the surface 1 million years ago is now buried under 3 kilometers of sediment. 3 kilometers. That is a greater distance than humanity has excavated in its deepest mines. If a civilization built its coastal cities 100 million years ago, they would now be buried under 30 kilometers of sedimentary rock, 30 kilometers below the surface, compressed into rock strata, indistinguishable from natural geological formations. And that is just in areas of high sedimentation. In the deep oceans, far from the coasts, sedimentation is much slower, but equally relentless. Even in the quietest abyssal plains, approximately 1 centimeter of sediment accumulates every 1,000 years. It seems little, but on geological timescales, it is devastating. Any artifact that fell to the ocean floor 100 million years ago would now be buried under 1 kilometer of oceanic sediment. But even being buried does not guarantee preservation, because the Earth has other tricks up its sleeve. Subduction. This is perhaps the most dramatic process of all the terrestrial mechanisms of oblivion. In subduction zones, where one tectonic plate slides beneath another, the ocean floor literally disappears into the depths of the Earth's mantle. And when I say disappears, I mean it melts, disintegrates, turns into liquid magma that may eventually return to the surface as lava, but completely transformed, with no memory whatsoever of what it once was. Approximately every 200 million years, the entire ocean floor of the planet is recycled in this manner. Everything, every square centimeter of the seafloor, along with everything it contains, disappears into the Earth's igneous depths and emerges transformed as new oceanic crust. That means that any evidence of civilizations that fell into the ocean more than 200 million years ago no longer exists. It is not buried, it is not hidden, it is not preserved in some geological archive waiting to be discovered. It simply no longer exists. It is being literally digested by the planet. But, you might argue, what about the continents? The continents are more stable, right? Continental plates do not subduct. They are too light, too buoyant to sink into the mantle. It is true, but that does not mean they are perfect archives of the past. The continents have their own mechanisms of oblivion, equally effective, although slower. Continental volcanism, for example. When volcanoes erupt, they not only add new rock to the surface, they also bury everything that was there before. Massive volcanic eruptions, like those that occurred in the Siberian traps during the Permian extinction, can cover areas the size of entire countries, under kilometers of basaltic lava. The Columbia River volcanic province in the northwestern United States is a perfect example. Between 17 and 6 million years ago, a series of volcanic eruptions covered more than 200,000 square kilometers under layers of basalt that in some places reach 4 kilometers thick. 4 kilometers of volcanic rock that completely buried everything that existed in that region before the eruptions. If a civilization had flourished in that area 20 million years ago, it would now be buried under 4 kilometers of solid basalt, completely inaccessible and invisible to any future archaeologist. And then, there is continental tectonic activity. Continents may seem stable on human timescales, but on geological scales, they are in constant motion. They fracture, fold, elevate, sink. Mountain ranges arise from flat plains. Plains sink to become ocean basins. Rivers change course, eroding completely new valleys and abandoning others. The Appalachians, for example, are the eroded remnants of a mountain range that was once as high as the current Himalayas. Those original mountains formed approximately 400 million years ago, and since then have been reduced to less than 1/3 of their original height by continuous erosion. What chance would any artificial structure built in those original mountains have had of surviving 400 million years of erosion? Zero. Less than zero. But perhaps the most subtle and most powerful mechanism of oblivion of all is chemical alteration. Most of the materials we consider durable, metal, ceramics, even stone, are fundamentally unstable on the Earth's surface. They react with oxygen, with water, with the natural acids in the soil. They oxidize, hydrolyze, dissolve slowly into groundwater systems. Iron turns into iron oxide. Aluminum forms hydroxides. Even the hardest minerals, like quartz, gradually dissolve in slightly acidic waters. On geological timescales, even the hardest rocks are soluble. And here is the crucial point. All these processes, erosion, sedimentation, subduction, volcanism, tectonic activity, chemical alteration, operate simultaneously all the time everywhere on the planet. They are not occasional events. They are the normal state of the Earth. Our planet is fundamentally a processing machine that takes materials from the surface, crushes them, mixes them, transforms them, recycles them, reprocesses them in an endless cycle that has been operating for 4.6 billion years. In this context, the preservation of any evidence for more than a few million years is extraordinarily improbable. Not impossible, but extraordinarily improbable. The fossils we find, The geological strata we study, the rock formations we observe, are the exceptions, not the rule. They are the fortunate elements that by extraordinary combinations of circumstances manage to temporarily escape the planet's relentless processing. We begin to see the problem. It is not that the Earth is bad at preserving evidence of the past. It is that the Earth is extremely good at destroying evidence of the past. It is literally a machine designed to erase its own history and start anew. And if that is true, then the question is not, why do we not find evidence of previous civilizations? The question is, what kind of evidence could possibly survive this machine of oblivion for hundreds of millions of years? And how could we recognize it if we found it? That is a question that takes us to completely new territories, to ways of thinking about the past that challenge our most basic assumptions about what constitutes evidence and how it is preserved in deep time. Now that we understand how the Earth systematically erases the evidence of the past, we need to ask an even more unsettling question. When would it have been possible for previous civilizations to arise? There have been periods in the history of our planet where conditions were not only suitable, but ideal for the development of intelligent life. And the answer is as fascinating as it is disturbing. There have been not one, but multiple windows of opportunity, periods stretching over tens of millions of years, where conditions on Earth were perfect for the flourishing of civilizations, but which are now buried under layers of time so deep that we can barely begin to imagine what was lost in them. To understand these lost windows, we need to completely change our temporal perspective. We need to stop thinking in terms of human history and start thinking in terms of planetary history. We need to see the Earth not as a static stage where life gradually evolved towards us, but as a dynamic world that has gone through multiple golden ages, each with its own unique opportunities for the development of intelligence. Let us begin with the period that paleontologists call the Late Cretaceous, between 100 and 66 million years ago. This was the world of the dinosaurs at their peak, but it was also something much more extraordinary. It was a world of climatic stability and biological abundance that rivals anything we have seen before or since. During this epoch, global temperatures were approximately 10 degrees Celsius higher than today. There were no polar ice caps. The oceans were warm, from the equator to the poles. Sea levels were approximately 200 meters higher than today, which meant that vast areas of the continents were covered by warm, shallow seas, perfect for marine life. But the most extraordinary thing was the stability. This period of ideal conditions stretched for more than 30 million years. 30 million years of stable climate, resource abundance, explosive biological diversity. To put this into perspective, 30 million years is 100 times longer than we have existed as a species. What could have evolved in 30 million years of perfect conditions? Dinosaurs, of course, but also something else. During this period, some dinosaurs developed brains proportionally as large as those of the most intelligent modern birds. Troodon, for example, had an exceptionally large brain for its body size and characteristics that suggest considerable intelligence. Large, forward-facing eyes, for stereoscopic vision, hands with opposable fingers, complex social behaviors. Now, imagine an evolutionary lineage of Troodon that had not the 65 million years they actually had, but 100 million years of continuous evolution in stable conditions. Where would they have ended up? What level of intelligence would they have reached? What kind of societies would they have developed? We are not talking about science fiction. We are talking about completely plausible evolutionary possibilities. Intelligence is not an exclusive privilege of mammals. Birds are modern dinosaurs, and many bird species show levels of intelligence that rival primates. Crows use tools. Parrots can learn complex languages. Some species show behaviors that suggest an understanding of abstract concepts, like the mathematical zero. If the dinosaurs had had another 30 million years of evolution, is it really so impossible to imagine that some evolutionary lineage would have developed the capacity to manipulate their environment in ways that we would recognize as technological? But here is the truly unsettling thing. That window of opportunity closed abruptly. The asteroid that impacted the Earth 66 million years ago did not just extinguish the dinosaurs. It completely closed one of the most promising evolutionary windows in the planet's history. And it was not the only one. Consider the Carboniferous period, between 360 and 300 million years ago. This was a world radically different from ours, but equally fascinating in terms of evolutionary possibilities. Oxygen levels in the atmosphere were approximately 35% compared to the 21% today. This abundance of oxygen allowed for extremely efficient metabolisms and body sizes that would be impossible today. Insects reached gigantic sizes. Dragonflies with wingspans of 70 centimeters, millipedes the size of crocodiles, scorpions more than 1 meter long. But more importantly, during this period, the first vertebrates developed the ability to live completely on dry land. Amphibians evolved into reptiles. Terrestrial ecosystems became incredibly complex. This period lasted 60 million years. 60 million years of conditions that favored gigantism, metabolic complexity, and the diversification of terrestrial life forms. What forms of intelligence could have evolved in those unique conditions? Imagine arthropods the size of wolves, with nervous systems proportionally as complex as those of modern octopuses. Octopuses, after all, are incredibly intelligent, despite having a neurological architecture completely different from ours. They can solve complex problems, use tools, show behaviors that suggest a sophisticated understanding of cause and effect. What level of intelligence could the gigantic arthropods of the Carboniferous have reached if they had had 60 million years of continuous evolution in an oxygen-rich environment? What kind of societies could have developed creatures that combined the intelligence of octopuses with the social organization of ants, but at scales that allowed for complex manipulations of the environment? Again, this window closed abruptly. The end of the Carboniferous was marked by a period of global glaciation that dramatically changed planetary conditions. Oxygen levels fell, ecosystems completely restructured, giant life forms disappeared or were drastically reduced. But there is an even older and perhaps more intriguing window to consider: the Devonian period, between 420 and 360 million years ago. This was the age of fish, when the oceans teemed with diverse and sophisticated vertebrate life. During the Devonian, fish developed complex jaws, sophisticated sensory systems, elaborate hunting strategies. Some, like Dunkleosteus, reached sizes of up to 10 meters in length, but more importantly, for our purposes, some developed proportionally large brains and behaviors that suggested considerable intelligence. Modern sharks, which are essentially Devonian fish that survived until today, show surprising cognitive abilities. They can learn through observation. Some show complex social behaviors. They have sensory systems so sophisticated that they can detect extremely weak electric fields. Now multiply that intelligence by 60 million years of evolution in nutrient-rich oceans, and without significant competition from marine mammals. What forms of aquatic intelligence could have evolved? What kind of underwater technologies could they have developed? What evidence of such aquatic civilizations could have survived 400 million years of ocean floor recycling? And here we come to the truly disturbing point. We are not speculating about one or two lost windows. We are talking about multiple periods, each tens of millions of years long, where conditions were ideal for the development of forms of intelligence that could have reached levels of sophistication that we can barely imagine. The Ordovician, between 480 and 440 million years ago, when the first complex marine ecosystems were established and lasted 40 million years before being devastated by the first great mass extinction. The Silurian, between 440 and 420 million years ago, when life began to seriously colonize dry land and develop the first complex terrestrial life forms. The Permian, between 300 and 250 million years ago, when terrestrial ecosystems reached levels of complexity that would not be seen again until after the extinction of the dinosaurs. Each of these periods represents an evolutionary window of opportunity that stretched for longer than we have existed as a species. Each ended abruptly with a mass extinction that not only eliminated existing life forms, but also erased most of the evidence of what had evolved during those golden ages. And here is the question that should keep us awake at night. If civilizations had emerged during any of these lost windows, how would we know? What evidence could have survived? Not only the mass extinctions that closed those windows, but also the hundreds of millions of years of geological processing that followed. The unsettling answer is that we probably would not know. The evidence, if it exists, would be buried so deeply in the geological record, transformed so completely by planetary processes, that it would be practically unrecognizable as products of intelligence. Unless, of course, we know exactly what to look for and where to look, which brings us to one of the most fascinating questions of all. What kind of evidence could survive geological timescales? And have we already found it without realizing what it means? There is a white lie that we all learn when we are children about fossils. We are taught that fossils are like a history book of the Earth, where each layer of rock represents a page, and each fossil is a word that tells us the story of past life. It is a beautiful, comforting metaphor that makes us feel like we understand our planet's past. But like most white lies, it completely falls apart when you examine it closely. Fossils are not a history book. They are, at best, scattered pages from a book that has been torn up, burned, buried, excavated, rewritten, and torn up again thousands of times over millions of years. And from those scattered pages, we can only read a few words here and there, while the rest of the story remains forever lost to oblivion. To understand why we might not find evidence of previous civilizations, we need to understand exactly how fragmentary, how incomplete, how fundamentally misleading the fossil record is. Because if that record is so deficient at preserving evidence of simple life forms like mollusks and dinosaurs, what chance would it have of preserving evidence of something as delicate and complex as a technological civilization? The answer is profoundly unsettling. Let us start with the basic numbers. Paleontologists estimate that they have identified approximately 300,000 fossil species throughout the history of life on Earth. 300,000 species that have been catalogued, studied, classified. It sounds like a lot, right? But here is the problem. Biologists estimate that between 8 and 100 million living species currently exist on Earth, and that is just now, at this specific moment in planetary history. Over the 4.6 billion years of life on Earth, it is estimated that between 1 and 4 billion different species have existed. 1 billion species as a minimum, and we have found fossil evidence of 300,000. That means the fossil record preserves evidence of approximately 0.03% of all species that have ever existed, less than one species out of every 3,000. 99.97% of all life that has ever existed on Earth has disappeared without leaving any trace in the fossil record. Think about that for a moment. Let that figure settle in your mind. Less than 0.1% preservation. And that is for biological organisms that at least have hard parts, shells, bones, structures that have some chance of being fossilized under extraordinary circumstances. What chance would something artificial, something technological, have of being preserved in such conditions? But the situation is even worse than these numbers suggest, because preservation is not random. There are systematic biases in what is preserved and what disappears forever. First, there is the habitat bias. Organisms that live in environments where sedimentation is rapid, such as shallow seabeds or river deltas, have vastly more chances of being fossilized than organisms that live in mountains, forests, or environments where erosion is more common than deposition. This means that the fossil record is heavily skewed towards aquatic creatures and lowland organisms, while upland life is dramatically underrepresented. Imagine a civilization that preferred to build in mountains or high plateaus, far from floodplains and coasts. Their evidence would have a near-zero probability of preservation. Second, there is the temporal bias. Older rocks have had more time to be eroded, metamorphosed, or recycled back into the mantle. This means that the further back in time we look, the less complete the record becomes. For periods older than 500 million years, the fossil record is so fragmentary that enormous periods of time are represented by barely a few preserved localities worldwide. And here is the crucial point. Entire periods of tens of millions of years are represented by so few preserved rocks that if a civilization had existed during those periods, we might have absolutely no rock of the correct age in which to look for evidence. Third, there is the size and durability bias. Large creatures with hard parts have vastly more chances of being fossilized than small, soft-bodied creatures. This has created a distorted image of past life, where dinosaurs and other large vertebrates dominate our perception, despite the fact that they probably represented a minuscule fraction of the actual biomass in their ecosystems. More importantly, for our purposes, technological artifacts tend to be relatively small and made of materials that do not preserve well on geological timescales. Metal corrodes, plastic decomposes, even ceramics fracture and erode. The only materials that have any hope of long-term preservation are the hardest minerals, such as quartz, diamond, or certain synthetic crystals that a civilization would have to create specifically with long-term preservation in mind. How many of our current technologies are made of such materials? Practically none. Fourth, there is what we might call the recognition bias. Even if an artifact was somehow preserved, we would have to be able to recognize it as artificial. After millions of years of compression, chemical alteration, and deformation, what would a fossilized computer look like? A cell phone? An automobile? Probably like an irregularity in the rock, an unusual concentration of certain elements, a slightly different texture in the sediment, something a geologist would briefly examine and then discard as a minor curiosity, unimportant for the understanding of the history of life. But perhaps the most problematic bias of all is what we might call the duration bias. Fossils require very specific conditions to form: rapid death, immediate burial in sediments, absence of oxygen to prevent decomposition, and then millions of years without significant alteration. These are requirements so specific that fossilization is essentially an extraordinary statistical accident. For creatures that live normal lives and die normal deaths, the chances of fossilization are essentially zero. Only organisms that have the bad luck to die in the exact correct circumstances, in the exact correct places, at the exact correct moments, have any chance of preservation. Now, imagine applying this to evidence of civilization. A civilization that exists for millions of years, but whose individual artifacts have useful lives of decades or centuries. For any artifact to be preserved, it would have to be buried immediately after being created under the exact correct conditions for preservation, and then remain unaltered for hundreds of millions of years. The probabilities are astronomically small, and here is the most unsettling point of all. Even in the ideal case, where some artifact managed to be preserved, we would have to have the extraordinary luck to find it. The Earth's surface is enormous. Rocks of any specific age are irregularly distributed and often buried under younger rocks. Paleontologists have been systematically searching for fossils for less than 200 years and have excavated perhaps 0.001% of all the world's sedimentary rocks. In other words, we have examined a microscopic fraction of an already microscopic preservation of an already incomplete history. It is as if we tried to understand the history of human literature based on 3 random words found in the ruins of a library that was burned, rebuilt, burned again, and buried under a modern city. And yet, based on this fragmentary evidence, this accidental preservation, this absurdly small and inevitably biased sample, we reach conclusions about what was possible and what was not possible in the deep past of our planet. We begin to see the problem. It is not that we have evidence that previous civilizations did not exist. It is that we would not have evidence even if they had existed. The silence of the fossil record is not evidence of absence. It is simply silence. And that silence becomes even deeper when we consider that civilizations, unlike biological species, are not uniformly distributed across time and space. A species can exist for millions of years and spread across entire continents, which increases the chances that at least some individuals will be preserved under exceptional conditions. But a civilization might exist only in specific locations for relatively short periods. From a geological perspective, it could flourish for a few million years in a few specific regions and then disappear completely. The chances that some artifact of such a civilization would be preserved in the geological record and then rediscovered by modern archaeologists are vanishingly small. So, when we look at the fossil record and do not see evidence of previous civilizations, what are we really seeing? Evidence that such civilizations never existed, or simply confirmation that the fossil record is exactly as fragmentary and incomplete as we would expect it to be? The unsettling answer is that we cannot distinguish between these two possibilities based solely on the absence of direct fossil evidence. To resolve this question, we would have to look for other types of evidence, more subtle, but potentially more durable than ordinary fossils. We would have to look for the fingerprints that a technological civilization might leave in the very chemistry of the planet. And it turns out that when we start looking for such fingerprints, we find some rather unsettling things. There is something deeply unsettling about the regularity of the ice ages. For the last 2.5 million years, our planet has oscillated between glacial and interglacial periods, with the precision of a cosmic metronome. Each cycle lasts approximately 100,000 years, 80,000 years of ice, 20,000 years of warmth, and then it all begins again. But that regularity, that almost mechanical precision, hides a more disturbing truth. Each transition between ice and warmth is not simply a climate change, it is a complete transformation of the planet. It is the death of one world and the birth of a completely different one. And in those transformations, in those periodic rebirths, lies one of the most unsettling answers to our central question. Where is the evidence of previous civilizations? It was buried under kilometers of ice, crushed by continent-sized glaciers, and then washed into the ocean when that ice melted, over and over again for millions of years. To understand the magnitude of these cyclical erasures, we need to understand exactly what an ice age means from the perspective of evidence preservation. We need to see glaciers not as climatic curiosities, but as the most efficient demolition machines the planet has ever known. During the peak of the last ice age, just 20,000 years ago, ice sheets up to 4 kilometers thick covered most of North America and Europe. 4 kilometers. That is the height of an average mountain, but made entirely of solid ice, pressing down with a weight that literally caused the Earth's crust to sink beneath its mass. But the weight is only the beginning. Glaciers move, slowly sliding over the Earth's surface like gigantic sanding machines, dragging with them rocks the size of buildings, pulverizing everything in their path, until it becomes a mixture of sand and clay that geologists call glacial till. Imagine a civilization that had flourished in northeast North America 150,000 years ago during the previous interglacial period. Their cities, their monuments, their technologies, everything would have been there when the next glaciation began. And then, for the next 30,000 years, ice sheets kilometers thick would have slowly slid over the entire region, grinding everything into indistinguishable glacial sediment. When the ice finally retreated 20,000 years ago, no trace of that civilization would have remained. Not even a trace of the area's original topography would have remained. The glaciers would have carved entirely new valleys, created lakes where there were mountains before, redistributed enormous masses of sediment over thousands of kilometers. And this did not happen once. It happened repeatedly over and over again for millions of years. But here is what makes glaciations particularly devastating for the preservation of evidence. They do not just destroy what is on the surface, they also completely alter the patterns of sedimentation and erosion throughout the entire planet. During an ice age, the sea level drops dramatically because enormous volumes of water get trapped in the continental ice sheets. At the peak of the last glaciation, the sea level was approximately 120 meters lower than today. 120 meters. This means that vast areas that are now under the ocean were exposed as dry land for tens of thousands of years. Where would the civilizations of the Ice Age have built their cities? Probably on those exposed coastal plains, close to the oceans for trade and transport, but away from the regions devastated by glaciers. Those locations would have been ideal for the development of civilizations. And when the ice melted, what happened to those coastal cities? They were submerged under 120 meters of oceanic water. 120 meters of water that then filled with marine sediments over the next 20,000 years. If a civilization had flourished on the exposed coasts during the last ice age, its remains would now be buried under the ocean floor, beneath layers of marine sediment that make them completely inaccessible to conventional archaeology. But glaciations do not only affect the regions that are directly covered by ice, they alter global climate patterns in ways that completely transform the planet's surface. During the ice ages, wind patterns change dramatically. Ocean currents are altered. Regions that normally receive abundant rainfall turn into deserts. Areas that are normally arid become humid. Rivers change course. Lakes form and disappear. Entire ecosystems migrate thousands of kilometers. In those conditions, even the regions that are not directly affected by glaciers experience environmental changes so dramatic that the long-term preservation of evidence becomes extremely improbable. Structures erode under new wind and rain patterns. Sediments are redistributed. Landscapes are completely transformed. And then when the ice age ends, everything changes again. The glaciers melt in a period that, from a geological perspective, is practically instantaneous. All that trapped water in the ice returns to the oceans in a few thousand years, causing massive floods, completely altering drainage systems, depositing enormous amounts of glacial sediment in new locations. The result is that every transition between Ice Age and interglacial period is essentially a complete reboot of the Earth's surface, not as dramatic as a mass extinction, but severe enough to effectively erase any evidence of civilizations that had existed during the previous cycle. And here is the truly unsettling part. This cycle of construction and destruction has been operating for millions of years, long before humans appeared on the scene. The first major glaciations began approximately 2.5 million years ago. Since then, there have been at least 40 complete cycles of Ice Age and interglacial period, 40 opportunities for civilizations to emerge during the warm periods, and 40 complete reboots that erased the evidence of what had existed before. But the glaciations of the last 2 million years are not the only ones that have affected our planet. There have been periods of global glaciation much more severe in the deep past. Geologists have identified evidence of at least 5 major glaciation episodes in the Earth's history, some so severe that the entire planet turned into a snowball Earth covered in ice from the poles to the equator. The Huronian glaciation, between 2.4 billion and 2.1 billion years ago, lasted 300 million years. 300 million years of glacial conditions that would have made the preservation of any evidence of complex life virtually impossible. The Sturtian glaciation around 700 million years ago turned the Earth into a snowball for approximately 60 million years. When it ended, conditions were so different that life had to almost completely reinvent itself, which led directly to the Cambrian explosion of biological diversity. Each of these glaciation episodes represents not only a disruption in the development of life, but also a nearly complete erasure of any evidence of what had existed before. They are planetary reboots that make mass extinctions seem like minor events by comparison. And between these major episodes, there have been dozens of minor glaciation periods, each severe enough to fundamentally alter the Earth's surface and erase the evidence of the past. We begin to see the pattern. The Earth is not just a geological recycling machine operating on timescales of hundreds of millions of years. It is also a periodic cleaning machine, operating on much shorter timescales, systematically rebooting its surface every few million years through glaciations. If civilizations have arisen in the past, they would have had to survive not only occasional mass extinctions, not only the slow but constant processes of erosion and sedimentation, but also these periodic glacial reboots that systematically erase the evidence from the surface. It is as if our planet had multiple memory-erasing systems operating simultaneously. The great reboots of mass extinctions, the slow but constant erasure of geological processes, and the periodic reboots of glaciations, each operating on different timescales, but all working together to ensure that the evidence of the deep past is systematically eliminated. In this context, the question is not, why do we not find evidence of previous civilizations? The question is, how could any evidence possibly survive this arsenal of erasing mechanisms that have been operating for billions of years? And yet, there is evidence that survives. Rocks, fossils, geological formations that tell us about the deep past. But these are the extraordinary exceptions, the fortunate elements that manage to escape all the mechanisms of destruction for incredibly long periods. The question then becomes, what kind of evidence of previous civilizations could possibly be durable enough, resilient enough, to survive not only mass extinctions and geological processes, but also the repeated cycles of glaciation and deglaciation? That question leads us to even more speculative, but also more fascinating, territories, as we explore the more subtle ways a civilization could leave traces in the planetary record. There is an image that is ingrained in all our minds about the oceans, vast expanses of blue water that have remained more or less constant throughout history. We think of the continents as the changing parts of our planet, while the oceans are the stable, eternal backdrop against which the drama of terrestrial evolution unfolds. But this image is profoundly misleading. The oceans are not constant. Their levels rise and fall like the breathing of a sleeping giant, but on timescales so vast that they seem immutable from our human perspective. And in those risings and fallings, in those oceanic breaths that last millions of years, lies another crucial part of the answer to why we might not find evidence of previous civilizations, because it turns out that throughout the Earth's history, ocean levels have been much higher than they are now. Much higher. And when I say much higher, I mean hundreds of meters higher, enough to submerge vast portions of what we now consider permanent dry land. To understand the implications of this, we need to completely change our perspective on what is normal in terms of ocean levels. We need to stop thinking of current sea levels as the standard baseline and start understanding them as a historical anomaly, an unusually low moment in the long history of oceanic fluctuations. For most of the last 500 million years, sea levels have been between 50 and 200 meters higher than today. During some periods, such as the Cretaceous, they were up to 300 meters higher. 300 meters. That is the height of a 90-story skyscraper. What does this mean in practical terms? It means that vast areas of what are now the United States, Europe, Asia, Africa, would have been completely submerged under shallow, warm oceans for most of the history of complex life on Earth. The interior of North America would have been a shallow sea, extending from the Gulf of Mexico to the Arctic. Europe would have been an archipelago of scattered islands in a tropical ocean. Large portions of Asia would have been underwater. Australia would have been considerably smaller. But here is the truly unsettling part. Those submerged areas, those lost continents under ancient oceans, were not desolate wastelands. They were some of the richest and most productive environments on the planet. Shallow, warm oceans are perfect incubators for complex life. They are environments where biodiversity explodes, where ecosystems become incredibly sophisticated, where if intelligence were to arise, it would have the best possible conditions to flourish. And where would the evidence of any civilization that had arisen in those regions during the periods of high ocean level be now? Buried under kilometers of oceanic sediment, completely inaccessible to conventional archaeology. But the problem is even more complex than this image suggests, because ocean levels do not just rise and fall gradually. They also fluctuate in cycles, and those cycles operate on multiple timescales simultaneously. There are the short-term cycles related to the ice ages that we have discussed previously. During glaciations, the sea level drops because water gets trapped in the continental ice sheets. During interglacial periods, it rises when that ice melts. These cycles operate on timescales of tens to hundreds of thousands of years. But there are also the long-term cycles related to deeper geological processes. Submarine volcanic activity can raise ocean levels by displacing water. Changes in the rates of sea floor spreading alter the volume of ocean basins. Movements of tectonic plates can create new ocean basins or close existing ones. These processes operate on timescales of millions to tens of millions of years and can cause fluctuations in sea level of hundreds of meters. The result is an incredibly complex pattern of oceanic risings and fallings that has been operating throughout the entire history of our planet. And each cycle, each fluctuation, represents an opportunity both for the development of civilizations and for their destruction and subsequent concealment. Consider, for example, what would have happened during the Cretaceous period between 146 million and 66 million years ago. During this period, ocean levels were consistently between 200 and 300 meters higher than today. The interior of North America was an ocean called the Western Interior Seaway. which stretched from the Gulf of Mexico to the Arctic Ocean. This sea was not a deep, hostile ocean. It was relatively shallow, warm, full of life. The conditions were perfect for the development of complex ecosystems. If intelligent life forms had evolved during this period, this interior sea would have been an ideal environment for the development of civilizations. But when ocean levels dropped at the end of the Cretaceous, what happened to any evidence of complex life that might have existed in that sea? It was buried under the sediments that were deposited when those waters retreated, and then under the additional layers of sediment that accumulated over the next 66 million years. If we excavated down to the correct sedimentary layers in the center of North America, we would find the remains of that ancient sea. We would find fossils of the marine creatures that lived there. But if there was also evidence of intelligence, of technological manipulation of the environment, it would be mixed with the normal marine sediments, virtually impossible to distinguish after so much time. And this is just one example. Throughout the Earth's history, there have been dozens of major oceanic transgressions, periods where sea levels rose dramatically and submerged vast continental areas. The Ordovician transgression, the Devonian transgression, the Jurassic transgression, the Paleocene transgression, each representing millions of years where conditions were ideal for the development of complex life in environments that are now completely inaccessible. But there is an even more unsettling aspect to these oceanic fluctuations. They do not just hide evidence of the past. They also create false impressions about where we should look for that evidence. When we think of civilizations, we naturally assume they would have developed on dry land, near the coasts for trade, but on solid, stable ground. That is, after all, the way all human civilizations have developed. But what if previous civilizations developed primarily in aquatic or semi-aquatic environments? What if the most favorable conditions for the development of intelligence were not the terrestrial plains that we associate with our own development, but the shallow, nutrient-rich oceans that covered much of the planet for most of its history? This is not as strange an idea as it might initially seem. Oceans offer several advantages for the development of civilizations. Resources are more uniformly distributed. Transport is easier. Climate changes are less severe due to the thermal capacity of water. Natural disasters, such as forest fires, volcanic eruptions, or meteorite impacts, have less catastrophic effects in aquatic environments. If intelligent civilizations had evolved in the shallow oceans of the Cretaceous or the Devonian, or any of the other periods of high ocean level, they would have had access to much more stable and resource-rich environments than anything available on dry land. And when those oceans retreated, their civilizations would not only have been buried under sediments, they would have been buried under sediments in what are now the most inaccessible parts of the continents, far from the current coasts, where our archaeological efforts are concentrated. How would you look for evidence of a civilization that flourished on the floor of what is now Kansas, buried under 3 kilometers of sediment, in layers that were deposited when that region was the bottom of a tropical ocean 100 million years ago? The unsettling answer is that you probably could not. The excavation costs would be prohibitive. Remote detection methods would not be effective at those depths. Even if you knew exactly where to look, it would be practically impossible to access those layers with current technology. And that assumes that we would know where to look, which is not the case. The paleogeographic maps that show the locations of ancient oceans are approximate reconstructions based on limited geological evidence. The details of exactly where the coastlines were, where the most productive areas were, where the development of civilizations would have been most probable, are largely speculative. We are in the position of future archaeologists trying to understand human civilization, but who only have access to the current ocean floors. They might find evidence of shipwrecks, submarine cables, perhaps some sunken oil platforms, but the great cities, The centers of civilization, the most important monuments, would all be on dry land, completely out of their reach. That is essentially the situation we find ourselves in when looking for evidence of previous civilizations. The most probable areas where such civilizations would have flourished, the richest and most stable environments of the geological past, are now buried under kilometers of sediment in the most inaccessible parts of the continents. And this leads us to an unsettling realization. It is not just that the evidence of previous civilizations has been destroyed by geological processes. It is that those evidences may be perfectly preserved, but in locations where we would never think to look, and where it would be practically impossible to access, even if we knew they were there. The oceans that rose did not just destroy the evidence of the past, they hid them in the most inaccessible places on the planet, under layers of time and sediment that make them virtually invisible to our current research methods. There is something profoundly disconcerting about the idea that the world map we know, with its familiar continents in their recognizable positions, is merely a temporal snapshot of a constantly changing configuration. The continents are not fixed landmasses. They are passengers on an epic journey across the planet's surface, sliding over the mantle like enormous rock rafts in a semi-solid ocean of magma. And in that journey, in that constant drift through eons of time, lies perhaps the most devastating mechanism of all for the destruction and dispersal of evidence of previous civilizations. Because continental drift does not just move continents, it fragments them, disperses them, crushes them, reassembles them into completely new configurations over and over again for billions of years. To understand the magnitude of this destruction, we need to completely free ourselves from our perception of continents as stable, permanent entities. We need to see the Earth's surface for what it really is, a gigantic jigsaw puzzle whose pieces are in constant motion, colliding, separating, merging, fracturing in a process that has been literally rewriting the world map throughout the planet's entire history. 200 million years ago, all the continents on Earth were joined in a single gigantic landmass called Pangaea. But Pangaea was not the beginning of the story. It was merely the most recent configuration in an endless series of supercontinents that had formed and separated throughout geological history. Before Pangaea existed Pannotia 600 million years ago. Before Pannotia existed Rodinia 1 billion years ago. Before Rodinia existed Columbia 1.8 billion years ago. And before Columbia other continental configurations, whose names we have lost in the vastness of deep time. Each of these supercontinents formed through massive collisions between smaller landmasses, collisions that lasted tens of millions of years, and that literally welded separate continents into a single gigantic entity. And then each one fragmented again. It separated along new rupture lines, dispersing its pieces across the globe to eventually regroup in new configurations. But here is what makes this particularly devastating for the preservation of evidence. These are not clean, orderly separations. They are violent and chaotic processes that involve a massive deformation of the Earth's crust. When continents collide, rocks fold, fracture, metamorphose under extreme pressures and temperatures. Mountain ranges rise kilometers into the air. Sedimentary basins are compressed until the rocks transform into completely new forms. Fossils that once preserved evidence of ancient life are distorted beyond recognition or completely destroyed. And when continents separate, the process is equally destructive. Massive volcanism accompanies the continental breakup, covering vast areas under kilometers of basaltic lava. New oceans open up between the separating land masses, submerging the rupture areas under oceanic water. Drainage systems are completely altered, changing the patterns of erosion and sedimentation throughout the entire continent. Imagine a civilization that had flourished on Pangaea 200 million years ago. Its evidence would now be scattered across all modern continents, fragmented by the processes of continental breakup, deformed by the collisions of tectonic plates, buried under layers of volcanic rock, or submerged under oceans that did not exist when that civilization was alive. How would you recognize evidence of a unitary civilization if its fragments were now scattered between North America, Europe, Africa, Asia, Australia, and Antarctica? How would you connect artifacts found in the eastern United States with related artifacts now buried under the mountains of Scotland, when those two regions were connected 200 million years ago, but have been separated by an ocean for all of human history? But the problem is even deeper than simple geographical dispersal. Continental drift operates on multiple scales simultaneously, creating nested levels of fragmentation and destruction. At the largest scale, we have the supercontinent cycle, where all landmasses join and then separate in periods of approximately 500 million years. But within those large cycles, there are smaller and more frequent movements. Individual tectonic plates are in constant motion, sliding over each other, colliding, separating, changing direction. A plate that is moving north for 50 million years can change direction and start moving east. Two plates that have been separating can start to converge. A subduction zone can change location, completely altering the patterns of volcanic and seismic activity. These changes in plate movements create what geologists call tectonic events, periods of intensive deformation that can last millions of years and that fundamentally alter the structure of entire continents. During the Alleghanian tectonic event, between 320 and 260 million years ago, the continent that would eventually become North America was completely restructured. Entire mountain ranges rose and eroded. Sedimentary basins that had been accumulating sediments for tens of millions of years were compressed, folded, and metamorphosed. The geology of the entire continent was rewritten. If a civilization had existed in North America before that event, its evidence would have been completely obliterated by tectonic deformation or altered to the point of being unrecognizable. And this type of major tectonic event has occurred repeatedly throughout the history of every continent. North America has experienced at least 5 major mountain-building episodes in the last 500 million years. Europe has experienced even more. Asia, being a collection of continental fragments that have welded together over time, has an even more complex tectonic history. Each of these events represents a fundamental alteration of the continental crust, a period where evidence of the past was destroyed or transformed beyond recognition. But perhaps the most unsettling aspect of continental drift is how it creates false impressions about the continuity of terrestrial environments. When we look at a modern map, we see continents that seem to have been in their current positions forever. We see oceans that seem permanent, mountain ranges that seem eternal. But this perception is profoundly misleading. India, for example, has not always been part of Asia. 100 million years ago, it was an island continent sliding north across the ocean that separated Africa from Asia. When it finally collided with Asia 50 million years ago, the collision was so violent that it pushed the Himalayas kilometers into the sky and created the Tibetan Plateau, the largest elevated region in the world. Any evidence of life that had existed in the collision zone was completely obliterated by the impact, and any evidence that had existed in India before the collision is now distributed across thousands of kilometers, from the Himalayan mountains to the Ganges plains, deformed by tectonic compression. Australia provides another fascinating example. For most of the last 200 million years, Australia was connected to Antarctica as part of a southern supercontinent called Gondwana. It separated from Antarctica just 35 million years ago and has since been drifting north. But that separation was not a simple event. It involved massive volcanism, the opening of new ocean basins, and the complete alteration of climate patterns on both continents. Any evidence of civilizations that had existed in the rupture zone between Australia and Antarctica is now buried under the Antarctic ocean floor, completely inaccessible. And here is the crucial point. These processes are not rare events of the distant past. They are happening right now. Africa is separating along the East African Rift Valley. In a few million years, East Africa will have completely separated from the rest of the continent, creating a new ocean. California is sliding north along the San Andreas Fault. In 50 million years, Los Angeles will be north of San Francisco. Continental drift is a continuous, relentless process that is constantly rewriting the planet's geography. And in that constant rewriting process, the evidence of the past is fragmented, dispersed, deformed, or destroyed. We begin to see the magnitude of the problem. We are not looking for evidence of previous civilizations on a static planet, where that evidence has remained in the same place for millions of years. We are looking for it on a dynamic planet, where the continents themselves are in constant motion, where the geography is continuously rewritten, where the evidence of the past is constantly mixed, dispersed, and transformed by tectonic processes that operate on geological timescales. In this context, the question is not, why do we not find evidence of previous civilizations in orderly and recognizable configurations? The question is whether such evidence could even exist in a coherent form, after having been processed through hundreds of millions of years of continental drift, plate collisions, and tectonic deformation. And that question leads us to the last and perhaps most devastating of all the destruction mechanisms that our planet has deployed throughout its history. Cosmic impacts that do not just alter the planet's surface, but completely reshape it. There is an unsettling fragility in our planetary existence that we rarely contemplate in daily life. We are navigating through space on a small blue rock, surrounded by a vast field of cosmic debris that includes asteroids, the size of mountains, comets laden with ice, and rocky fragments that wander aimlessly through the solar system for billions of years. And occasionally, very occasionally, our paths cross. When this happens, the result is not simply a collision. It is a complete rewriting of planetary history. Cosmic impacts are not events that add new chapters to the Earth's history. They are events that erase entire chapters, that tear complete pages from the geological book, that reset the evolutionary clock and force life to start anew from fundamentally altered configurations. And in those cosmic reboots, in those violent rewritings of the planetary surface, lies perhaps the most devastating mechanism of all for the elimination of evidence of previous civilizations. To understand the magnitude of these events, we need to free ourselves from the reassuring image of impacts as rare and minor events. We need to see our planet for what it really is, the target of a constant bombardment that has been operating throughout its entire history. A bombardment that occasionally includes projectiles, large enough to fundamentally alter the geology, climate, and biology of the entire world. The most famous impact, of course, is the one that created the Chicxulub crater 66 million years ago. An asteroid, approximately 10 kilometers in diameter, impacted the Yucatan Peninsula with an energy equivalent to several billion nuclear bombs. The impact created a crater 180 kilometers in diameter, launched molten rock into Earth orbit, initiated global forest fires, and covered the entire planet under a layer of debris that blocked sunlight for months. But here is what makes this event particularly relevant to our question. It did not just extinguish the dinosaurs. It physically altered the surface of the entire planet in ways that erased evidence of what had existed before. The impact energy was so great that it created seismic waves that traveled throughout the planet, causing massive earthquakes and volcanic eruptions on the opposite side of the world. Debris launched into the atmosphere fell as a global rain of molten rock, igniting forests on every continent. Tsunamis generated by the impact swept the coasts of North America with waves hundreds of meters high. Within hours, the entire surface of the planet was altered. Any artificial structure that had existed in the areas affected by the tsunamis would have been completely destroyed. Any evidence of civilization that had been on the surface would have been buried under layers of impact debris or incinerated in the global fires. And this was just one of many major impacts that have occurred throughout the Earth's history. The Vredefort impact 2 billion years ago involved a projectile approximately 20 kilometers in diameter that created a crater more than 300 kilometers in diameter in what is now South Africa. The energy released was approximately 100 times greater than that of the Chicxulub impact. The shock waves from this collision altered the geology of much of southern Africa, creating rock formations that are still visible today. The Sudbury impact, 1.8 billion years ago, created one of the largest known impact structures on Earth, with a diameter of approximately 250 kilometers. The impact was so intense that it literally melted the bedrock to depths of several kilometers, creating a sheet of molten rock that took millions of years to completely cool. The Manicouagan impact, 215 million years ago, created a crater 100 kilometers in diameter in what is now Quebec. This impact roughly coincides with one of the minor mass extinctions of the Triassic period, suggesting that it may have contributed to a significant restructuring of global ecosystems. Each of these events represents not only a local catastrophe, but a global alteration of planetary conditions. And these are just the large impacts that have left craters well preserved enough to be identified after millions or billions of years of erosion and tectonic activity. How many other major impacts have occurred but have been erased by geological processes? How many craters have been buried under sediments, destroyed by volcanism, or fragmented by continental drift to the point of being unrecognizable? Astronomers estimate that impacts capable of causing global extinctions occur approximately every 100 million years. Impacts large enough to significantly alter regional ecosystems occur much more frequently, perhaps every few million years. In the 4.6 billion years of Earth's history, this means there have been at least 46 impacts the size of the Chicxulub event, and possibly thousands of minor, but still significant, impacts. Each of these events represents a massive interruption of any civilization development process that might have been occurring at that time. But there is an even more unsettling aspect to cosmic impacts that goes beyond their immediate devastation, their long-term effects on the preservation of evidence. When a large asteroid impacts the Earth, it does not just destroy what is on the surface at the moment of impact, it also fundamentally alters the geological processes that determine what evidence of the past will be preserved for the future. Massive impacts alter global climate patterns for periods that can extend for millions of years after the initial event. They change ocean circulation patterns, alter atmospheric composition, modify the types and rates of erosion and sedimentation throughout the entire planet. The result is that the periods following major impacts are characterized by unusual geological conditions that can be particularly destructive to the preservation of evidence from the past. After the Chicxulub impact, for example, the planet experienced a period of several million years of intensified volcanism, dramatic climate changes, and ecosystem alteration. During this period, erosion rates were much higher than normal, and sedimentation patterns were profoundly altered. Any evidence of civilizations that had survived the initial impact would have faced extraordinarily hostile geological conditions for the next millions of years. Structures that might have survived buried would have been subjected to accelerated erosion, intensified chemical alteration, and altered sedimentary processes that would make their long-term preservation even more improbable than usual. And here we come to a particularly disturbing realization. Cosmic impacts do not just destroy civilizations, they also destroy the evidence that they ever existed. Imagine that a previous civilization had developed technologies advanced enough to leave durable markers of their existence, signals designed specifically to be detected by future civilizations. Ultra-durable synthetic materials, large-scale geological modifications, even alterations in the orbit of minor planets or moons. A large enough impact could destroy or alter even that seemingly permanent evidence. Synthetic materials would melt in the extreme temperatures generated by the impact. Geological modifications would be obliterated by the shockwaves. Orbital alterations would be disturbed by changes in the planet's gravitational field, caused by the massive redistribution of material during the impact. In other words, cosmic impacts do not just eliminate ordinary evidence of previous civilizations, they also eliminate extraordinary evidence, the evidence that advanced civilizations might have created specifically to survive all the other destruction mechanisms we have discussed. But perhaps the most unsettling aspect of all this is the regularity of these events. Cosmic impacts are not rare cosmic accidents. They are part of the normal functioning of the solar system. They are as inevitable as mass extinctions, as predictable as glaciations, as constant as continental drift. Our solar system is full of cosmic debris that represents a continuous threat to all the planets. The asteroid belt between Mars and Jupiter contains millions of objects, some the size of mountains. The comet cloud surrounding the solar system contains trillions of icy objects, any of which could be perturbed into an Earth-crossing orbit. And these are not the only dangers. Gravitational perturbations from stars passing close to the solar system can alter the orbits of comets and asteroids, sending them towards the inner planets. Supernova explosions in nearby stars can bombard the solar system with radiation that destroys protective atmospheric layers. Even the movement of the solar system through the galaxy periodically exposes it to regions of higher cosmic debris density. In this context, the preservation of evidence of civilizations over periods of hundreds of millions of years is not only improbable due to terrestrial geological processes, it is also improbable due to the statistical inevitability that the planet will be repeatedly hit by objects large enough to fundamentally alter its surface. And that leads us to the final question, the deepest and most disturbing of all. After examining all these destruction mechanisms, all these processes that systematically erase the evidence of the deep past, what conclusions can we draw about our place in cosmic history? Are we truly the first, or are we simply the most recent in a long chain of civilizations that have contemplated these same stars, that have asked themselves these same questions, that have reached these same unsettling realizations about the fragility and impermanence of everything we build? That question leads us to our final chapter, where we will explore the deepest implications of everything we have discovered on this journey through deep time. We have reached the end of our journey through deep time, and the view from here is both humbling and extraordinary. We have explored the vast temporal scales on which our planet operates, the multiple mechanisms that systematically erase the evidence of the past, the lost windows where intelligent life could have flourished for millions of years before disappearing without a trace. And now we must confront the question that has been whispering in the background of every chapter. What does all this mean for us? How does it change our understanding of who we are and what our place is in cosmic history? The answer is neither simple nor comforting, but it is profoundly important. For most of human history, we have lived with the implicit assumption that we are special, unique, the first to develop intelligence on our planet. This assumption is so deeply rooted in our thinking that we rarely question it directly. It is the foundation upon which we build our philosophies, our religions, our sense of cosmic purpose. But what we have discovered on this journey is that that assumption might be based not on positive evidence, but on an absence of evidence that is completely explainable without resorting to our uniqueness. We do not find evidence of previous civilizations, not necessarily because they never existed, but because the Earth is an extraordinarily efficient machine for erasing such evidence. The processes we have explored, mass extinctions, geological recycling, glaciations, oceanic fluctuations, continental drift, cosmic impacts, operate on timescales and with a thoroughness that makes the preservation of civilizational evidence over hundreds of millions of years statistically improbable. And this leads us to a profoundly humbling realization. We might not be the first. We might simply be the most recent in a long chain of intelligence experiments that our planet has been conducting for eons. Imagine for a moment that this were true. Imagine that during the last 500 million years, during each of the windows of stability between the great planetary catastrophes, life had experimented with intelligence, that civilizations had arisen, flourished for millions of years, developed technologies that we can barely imagine, contemplated these same stars, asked themselves these same questions about their cosmic loneliness, and then inevitably faced the same fate that we will eventually face. The next mass extinction, the next glaciation, the next cosmic impact, the relentless processes that systematically reset the planetary surface. In this scenario, we are not the unique protagonists of cosmic history. We are the latest actors in a play that has been performed many times before. Each performance unique and valuable, but each one eventually erased by the mechanisms of planetary oblivion that we have explored. Is this a depressing perspective? Perhaps for some, the idea that we might not be unique, that our greatest achievements might eventually be erased as completely as those of previous civilizations, might seem like a denial of the meaning and importance of everything we do. But there is another way to look at this, a perspective that finds depth and meaning precisely in our possible non-uniqueness. If we are part of a long chain of civilizations, then we are the heirs of a cosmic tradition of intelligence that extends far beyond our brief existence. We are the most recent expression of an impulse towards understanding, towards contemplation, towards the search for meaning that has been operating on our planet for eons. Every previous civilization, if they existed, would have faced the same fundamental challenges that we face: how to understand our place in the cosmos, how to find meaning on timescales that dwarf our individual lives, how to create something of lasting value in a universe that seems dedicated to erasing the traces of the past. And each one would have arrived at its own answers, would have created its own forms of art and science and philosophy. It would have experienced its own versions of love and loss, hope and despair, triumph and tragedy. In this perspective, we are not alone in time. We are part of a cosmic conversation that has been developing for millions of years, even if we cannot hear the voices of our predecessors, because their words have been erased by the winds of deep time. But there is something even deeper to consider. If we have arrived at these realizations about the mechanisms of planetary oblivion, it is likely that previous civilizations, if they existed, also arrived at similar conclusions. They too would have understood the fragility of long-term preservation. They too would have contemplated their own impermanence. And that raises a fascinating question. What would they have done with that knowledge? One possibility is that they would have worked to create evidence specifically designed to survive the mechanisms of planetary destruction. Messages encoded in the crystal structure of ultra-durable synthetic materials, subtle modifications in the orbits of solar system objects, alterations in the isotopic composition of certain elements, signals so deeply integrated into the physical structure of the planet that they would survive even the most dramatic reboots. If such signals exist, we have not found them yet. But that does not mean they are not there. We might simply not know how to look for them, or not have the technology to detect them, or not have yet developed the conceptual frameworks to recognize them when we find them. Another possibility is that previous civilizations would have arrived at a different conclusion, that physical permanence is not the most important kind of legacy that can be left, that the real value of intelligence is not in the artifacts it produces, but in the patterns of thought, the ways of experiencing reality, the ways of finding meaning and beauty in existence. In this perspective, the real legacy of a civilization would not be something that could be preserved in rocks or crystals, but something more subtle and more durable. The contribution to the very evolution of intelligence, the addition of new possibilities to the repertoire of ways in which the universe can know itself. Every civilization that arises contemplates the cosmos, creates art and science and philosophy, experiences the full range of conscious experiences, adds something unique and irreplaceable to the cosmic totality of what has been possible, and that something cannot be erased by any geological process, because it exists at the most fundamental level of reality, in the fact that it occurred, that it was experienced, that it contributed to the total richness of what the universe has contained. This perspective finds profound meaning, not in permanence, but in participation, not in preservation, but in the experience itself. We are significant, not because we are unique or because our achievements will endure forever, but because we are part of the process by which the universe becomes conscious of itself, experiences itself, understands itself. And if that is true, then every moment of contemplation, every act of understanding, every experience of beauty, or love, or wonder, is an irreplaceable contribution to something much greater than ourselves. But perhaps the most important implication of everything we have explored is this: the recognition of our possible non-uniqueness should make us more humble, but also more determined. More humble, because our achievements might not be unique in cosmic history. More determined, because, unique or not, they are still our achievements, our opportunity to contribute to the cosmic conversation, our moment to participate in the great experiment of intelligence. If we are the first, then we carry the extraordinary responsibility of being the pioneers of planetary intelligence. If we are not the first, then we carry the equally extraordinary responsibility of continuing a tradition that extends far beyond us in time. In either case, the answer is the same. We must make our participation in this cosmic conversation as rich, as profound, as meaningful as possible. We must contemplate, create, explore, love, understand, experience the full range of what it means to be conscious in a cosmos that has been developing the capacity for consciousness for billions of years. And we must do so with the humility of knowing that our moment in this conversation is limited, but also with the determination to make every moment count, every experience significant, every act of understanding a contribution to something much greater and more lasting than ourselves. Because in the end, whether we are the first or the last or simply the next in the chain, we are part of something extraordinary, the process by which the universe becomes conscious of its own beauty, complexity, and meaning, and that, no matter how many other civilizations may have participated in this process before us, is something worth celebrating, protecting, and continuing with all the wisdom, creativity, and determination we can muster. So the next time you look at the stars, remember, you might not be looking at an empty cosmos, waiting for intelligence to emerge for the first time. You might be looking at a cosmos that has been experimenting with intelligence for eons, where your contemplation is the most recent in a long chain of similar moments, where your wonder is the newest echo of a wonder that has been resonating through deep time for much longer than we can imagine. And if that thought makes you feel small, remember this, too. You are the way the universe is knowing itself at this specific moment, in this specific place, in a way that has never happened before and will never happen again in exactly the same way. That makes you not only significant, but unique and irreplaceable. No matter how many other intelligences may have contemplated these same stars in the deep past of our planet. Thank you for joining me on this journey through deep time. If these types of slow, contemplative explorations are your thing, I would be grateful if you would subscribe to Dato Terra. Because in a universe where intelligence might be much more common than we think, but where every expression of that intelligence is unique and valuable, every moment of shared understanding becomes something precious. And who knows, perhaps one day we will develop the technologies or the conceptual frameworks to detect the subtle signals that previous civilizations might have left for us. Until then, we have enough to contemplate in the simple fact that we exist, that we are conscious, that we can ask ourselves these questions about our place in the immensity of time and space. That is more than enough for a lifetime of wonder.